Hey guys, it's Mr. Bison and welcome to Bison Maths. If you are new to the channel, I have been a maths teacher since 2010, pretty much just A-level maths and further maths, and I am going to, in today's video, take you through the top 10 hardest questions for A-level maths, and that's specifically focusing on questions that are from Edexcel. And I'm kind of wondering, maybe I should have renamed this the top 10 worst performed on questions that there are, because that's how I've gathered these questions. These are the ones that have got the lowest average mark from people that sat these papers. I've updated this since the previous video, so now it includes everything up to 2022. There are no AS questions, and it's just everything from the Edexcel pure papers. And if you like this video, I'll think about doing it for mechanics and for statistics and maybe for some further math stuff as well. Now, I want to be straight up with you about where this has come from or how I've actually gone about finding these top 10 questions. Well, rather than looking at individual parts of questions and their average marks, I've looked at entire questions and grouped all of that together. So you're unlikely to see any particular really tough parts at the end of a question. It's more that the questions are consistently challenging. The second thing I want to say, explaining the data a bit more, is thinking about each year that these papers were being sat and what might have been going on in that year. So in 2018, you're not going to see any of those questions in this top 10 list, and that's because this was pretty much just sat by further maths students. That was the first year the A-level was running, and you find that sometimes people do A-level maths in year 12 and then A-level further maths in year 13. I then want to talk to you about the 2020 and 2021 series. Well, it was COVID, right? So there was no exams that were being sat externally by schools, but there were private candidates. So when we see those questions, we have to bear in mind they were not sat by thousands and thousands of people. The sample size was much smaller, and it's probable that those people didn't have as much support in their preparation for the exams. So you're probably going to see some 2020 and 2021 papers in this video. And then the last thing I wanted to point out was the 2022 series. Now, I don't know if you remember this, but the year 13 students that year were given something called advance information, which basically gave them a heads up about what topics were going to be coming up in what paper. So maybe that would have given them an advantage, maybe not. See if any of the 2022 questions come up in this. And then the last thing I want to talk to you about is the question number. Again, I'm trying to go down into that data and think what's really going on in these questions. You'll find, and you can see the scatter plot that's on the screen, the later the question in the exam paper, the poorer the performance. But my question is it because the question is much harder, or is it because people ran out of time and didn't get a chance to do it? And we'll have a little think about some of those questions that pop up and see whether we think it's because it was a hard question or whether it's because people had run out of time. Last thing on that scatter plot, you'll see what I said about the 2018 questions. Those green dots are all much higher up, probably because the further math students did quite well in that. And last of all, there's a pretty clear evidence of some negative correlation there. The higher the question number, the lower the average percentage in each question. So without further ado, let's get going on these top 10 questions for A-level maths. Okay, so I should also mention that I've linked in the description a blank version of this PDF, as well as this version where I've got everything annotated, just in case you wanted to have a go at the questions yourself first, and then you can always compare it to my answers. And I'm going to go a little bit quicker than I did in the previous video on this, just in the interest of getting through as much content as we can do. And I've just basically written out my answers already to see if we can speed things up a little bit. So the first one that comes in at number 10 is a differential equations question. This is from a COVID paper, and the average mark in this paper, in this question, was 23.6%. So if you want to pause it and read through it, you can do, but I'm going to just kick in straight away. So we've got here a large spherical balloon is deflating, and they're telling us about the time and the volume, and they're saying that the volume is decreasing at a constant rate. And then suddenly we want to say this thing here, which is about how the radius is changing, the rate of change of the radius. And they later on tell us some other things, but we don't need that because we're just looking at part A here. Well, because we're going to try and find out what dr dt is, we have to use something called connected rates of change. And that means where you separate this derivative that we've got here, or this differential, into a dr dv and a dv dt. And what you'll notice is those dv's kind of essentially cancel out there. So we need to find dv dt and dr dv. What I've done here is I've written down the formula for the volume of a sphere. That's something that people should know, but I think maybe tripped people up in this question. And if you differentiate this, you come up with 4 pi r squared. So I've now got this part by taking its reciprocal, dr dv and dv dr. Then I also have dv dt, which is the constant rate that it's leaking out. So I've got that dv dt is minus c. It's minus because it's leaking out there. So combining those together, I come up with this part here, and if I let k be equal to c over 4 pi, I do come up with the minus k over r squared as they wanted. So that was just those first 3 marks. Now the second part of the question, which is to solve the differential equation, given some of this extra information that they've got, that it started off with a radius of 40 and after 5 seconds had a radius of 20, it's just literally solving a differential equation. So the way we do that is we send the r squared term up with dr and we put the dt up here. We simply integrate on both sides, so we get a third r cubed equals minus kt plus c. And then all I'm doing down here is just substituting in the fact that when it started off, the radius of the balloon was 40, which tells me that c is this value, and that 5 seconds later, the radius of the balloon was 20, which gives me a value of k as 11,200 over 3. So I can just put it straight back into this form that we've got up here. We come up with this equation. I've multiplied it all by 3 just to make it look a bit nicer. And that's it for that part of the question. So that was a big 5 marks for just solving the differential equation. And then the last part, I don't think people would have done very well on either. It says find the limitation on the values of t for which the equation in part B is valid. Well, for something to be valid in this particular scenario that we've got here, I want the radius of the balloon to be bigger than 0. Otherwise, how could you have a negative radius? So that's all I've done down here, as I've said, the radius has got to be bigger than 0, which means this thing has got to be bigger than 0, which means that t is less than 40 over 7. So the amount of time it's valid for is when it starts off all the way up to 40 over 7. After that, the model predicts that there is a negative radius for the balloon, which kind of doesn't make any sense. Okay, so let's have a look at number 9. Number 9 is a differentiation question from 2020 paper 2, another COVID paper, and a very low percentage of 23.3% here. So we've got this function, and the function is in terms of some ln functions here, and they've told us about the domain that x is greater than 0 and x is not allowed to be equal to k. First of all, we're going to deduce the value of k. Well, things are not allowed to be equal to something, usually when we're doing division by 0. So I'm going to investigate what happens if x was k and this thing was 0. So that's what I've got down here. I've said if x was k and the whole thing was 0, rearranging that, you get ln k is 2, so k is e squared. So the value that k is e squared, x cannot be e squared. Then I'm going to do the tricky part of this question, which is to show that the derivative of this function, this is not the inverse, this is the derivative, is greater than 0 for all values of x in the domain of g. So I'm going to concentrate on the fact that x is greater than 0, and I'm going to differentiate it. So I'm going to use the quotient rule. My u is this, and my v is this. I'll differentiate them both, so this goes to 3 over x and this goes to 1 over x. Obviously the minus 7 and the minus 2, they just go. And here is my quotient rule that I've got here. It's vu dash minus uv dash divided by v squared. Subbing in all of this stuff that we've got into the formula for the quotient rule, we come up with this part. In this line down here, all I've done is just expanded the brackets. And what we notice is this 3 over x ln x and this minus 3 over x ln x, they just cancel out with each other, leaving us with these two things simplifying to just minus 6 plus 7, that's just 1 over x that we've got here. Now we need to try and sort of prove why this thing is always greater than 0. Well, having a look at this, we need to do it for the fact that x was greater than 0. I mentioned that part at the beginning. So if this thing is greater than 0, I want to see what happens to the numerator and the denominator. Well, if x is greater than 0, 1 over x is greater than 0. And because ln x minus 2 is being squared, it's also greater than 0, because when things are squared, they have to be greater than 0. Or at least greater than or equal to 0, I suppose I should say there. Hence, the first derivative has always got to be greater than 0, because both of them are basically going to be positive numbers. And then the last part that we've got, it just says find the range of values of a for which the function is greater than 0. Now notice how it doesn't have the dash, it's just the original function. So I'm going to substitute a in here, and I'm just going to make this thing bigger than 0. So this is a pretty easy part. I've subbed in a, and I'm going to make this thing greater than 0. Well, that's just investigating when the numerator is greater than 0. So put the 7 on that side and divide by 3, and rearrange it using our log laws that we've got. So a is just greater than e to the power of 7 over 3. Now I was trying to think about why this one's in here. I think it's perhaps some of the confusion with the derivative that we've got here. Maybe some people thought it was an inverse function. And I'd also say this bit of algebraic manipulation down here is challenging, as well as this kind of written conclusion that we have as well. Okay, so let's see what's going on now with number 8. Number 8 that we've got here is Modelling with Trigonometry from 2022 paper 2, and it is 22.4%. So I'll quickly read through the question with you, because I think people don't like modelling, and I think this is why these questions are always appearing. So we've got figure 4 showing a sketch of a Ferris wheel, and then the height above the ground of a passenger is being modelled by this equation that we've got here. Figure 5 shows the sketch of that model for 1 revolution of the wheel. So that means the wheel is just going all the way around like that. They've told us about the maximum height of the passenger above the ground. So I think that must be corresponding to this part. The passenger is 1 meter above the ground when the wheel starts turning. And this whole process that we've got here is 720 seconds. Notice how there's this little extra bit up here. That's probably for it to kind of come back around again to the bit where the passenger gets back on. And we're just going to find an equation for the model. In other words, we're going to find out what A, B, and alpha are, exact value for A, exact value for B, and alpha to 3 significant figures. And then we'll do something in part B in just a second. So when we have a look at this, we've got this formula that they've told us, or this function that I should say, that the height is equal to that sine curve, but with the modulus signs. And obviously the modulus signs are the thing that's making it do that kind of bounce part. Now, it's a normal sine curve, but with some shifting stuff and some changes that have happened to it. First of all, the part that is outside the sine function is the thing that's going to kind of scale it up and down. We know it normally goes between 1 and -1, so we're going to be thinking about it scaling that amplitude, because it's like that kind of like a function transformation, right? And then when we have something that's in front of the variable, it's like this kind of thing. We know that it stretches it by a factor of 1 over b in the x direction, or in this case, in the t direction. And then the last part, the alpha, is going to do like shifting to the left or to the right. I don't know which way my camera is going to be going. Probably to the left it should be. Or maybe it would be that way for you guys. And that's because it's of the form of f of x plus alpha. You can see there plus alpha is the thing that's doing the shifting then. So all we need to do is just kind of analyse those things in this context. First of all, A must definitely be the maximum height. That must be the 50 that we've got there, okay? Because it normally scales it to 1. We want it to go all the way up to 50. And we know that it's 720 for 1 revolution. And on a sine graph, it's usually 180 degrees in this first kind of bit. But our one is taken 720 seconds. So what I'm saying is this kind of journey we've got here is 720 seconds. And it's basically half of a sine graph that we've got there. And half of a sine graph normally takes 180 degrees. So because we're going from 180 degrees to 720 degrees, that is stretching it by 4. But we have to remind ourselves that if we're stretching something by 4, the bit that's going to go in front of it would have to be the reciprocal of that. It would have to be a quarter. So we've now got that A is 50 and that B is a quarter. And then the last part we're going to try and do is find out what alpha is. And that uses the last bit of the bullet point, or maybe it was the second bullet point. Yep. The passenger is 1 meter above the ground when the wheel starts turning. So when the wheel starts turning, time is 0. The passenger is 1 meter above the ground. All I'm going to do is sub in that t is 0. I've got those other values that I know about, and that h is 1. If t is 0, we just get 1 equals 50 sine alpha. We don't need to worry about the modulus signs here because sine starts going upwards. Do 1 divided by 50 and do the inverse sign. Make sure you're in degrees mode because the question is in degrees. And we get 1.15 to 3 significant figures. Hence, this is our final formula that we've got here for it. And then the last part says, explain why an equation of this form would be a more appropriate model where d is a positive constant. So it's the same as this one, but we're adding something on. When you add something on, it shifts the graph up a bit. And because it's shifting the graph up a bit, it probably means the passenger is not going to do this weird part over here where it says the passenger is on the floor. It doesn't make sense to be on a Ferris wheel and to be bumping into the floor like that. So in this second model, the passenger now does not touch the ground, which is more realistic. Okay, so let's have a look now at number 7, which is a really tough question on implicit differentiation and particularly some stuff on points of inflection. Only 21.7% of people got this from 2020, paper 1. So first of all, we have this curve, and the thing we should notice is there is a mixture of x squared and y here. They're going to test a lot of different things. I think we should also notice it's question 15, so it's towards the end of the paper. People are probably quite stressed and running out of time as well. We're going to show that the first derivative is this. Interestingly, there's y here, but there's no y over here. So the way we go about doing this question, and hopefully you've tried something like this before, is we've got this, and I'm going to just differentiate this using some implicit differentiation, but also I'm going to have to use for this part the product rule. So I'm going to start off with differentiating my product rule, where I've got u is x squared and v is tan y. X squared goes to 2x, and tan y will go to sec squared y dy dx. That's the implicit differentiation. We know that tan goes to sec squared, and also you have to add in that extra dy by dx. So using the product rule, it's those two multiplied plus those two multiplied that we've got here, and obviously the 9 differentiates to 0. So I've rearranged this to make dy by dx the subject, subtracted that, and divided by x squared sec squared y. And now I want to go from something that has got y with it to something that only has x with it. And I've done that by using the original function that they've given us. So here I've said that tan y is 9 over x squared, which means I can replace this tan y with 9 over x squared. The sec squared y, I'm going to use my Pythagorean identity that 1 plus tan squared is equal to sec squared y. So I'll put that tan y in here and square it, and I'll come up with the fact that this is what sec squared y is equal to, and then I can just substitute it in here like this. All that's left to do is expand the brackets on the denominator and multiply this up here. And then to get rid of this fraction within a fraction, I'm going to times everything in the bottom by x squared, so I get x to the 4 and 81, and everything on the top by x squared, so I get minus 18x, which is the thing that they wanted us to come up with. So very, very challenging for those 4 marks, especially at question 15 here. They're really trying to test if people are those like A-star candidates. And then the last part says that prove that C has a point of inflection at this particular point, x equals the 4th root of 27, and only 3 marks. So point of inflection, we know, is when you differentiate it again and it needs to be equal to 0. So I'll do the quotient rule. I'm not going to go through all of this part here, but this is just the quotient rule on the previous thing that I've done, and we come up with this. Now this is the part that I think a lot of people dropped marks on, and I know when I first started teaching this, I didn't teach this properly, and I don't know of many people that did. So the point of inflection is going to be the case if the second derivative is equal to 0, and if there is a change of sign of the second derivative either side of that solution, because a point of inflection is something that is like this kind of shape, but you can technically have something where the second derivative is 0 at both of these points. This one is a point of inflection, this one is clearly a maximum point. The change of sign of the second derivative either side of it is the thing that actually shows it is a point of inflection. So I'm going to figure out the value of x when it's equal to 0, and that actually turns out to be the 4th root of 27. And then to get that final mark, we need to say that when x is lower than that, the second derivative is less than 0. You can just imagine substituting something that was slightly smaller than the 4th root of 27 in here, and it becomes negative. And similarly, when x is bigger than that, the second derivative becomes bigger than 0, meaning it becomes a positive. So we've got this point of inflection where the second derivative is less than 0, and then it's greater than 0, meaning it's going from concave to convex or vice versa. And so we've actually got that point of inflection, and we do need that conclusion statement there. So not many people will have got that mark, which will have had a big impact on how people did in part B of the question. Okay, so question 6, and finally we've got our first one that is from the 2022 paper 1, and it is 21.6% as an average mark here, and this is parametric integration. Now, not only is this question really, really difficult, but the advanced information, I think, played a role in this appearing in this list. The advanced information in 2022 did not mention parametric integration. They had previously mentioned parametric differentiation, and I think for this question they just said integration. So because they'd said parametric differentiation and they didn't say parametric integration, nobody thought parametric integration was coming up. And then these kids came out of the exam and they were like, "Sir, I cannot believe it. There was parametric integration in there," and I was not very happy, particularly because it's question 16 and it is tough. So yeah, imagine doing your first exams for a couple of years and you come into the exam and your last question is this one that we've got here. So this one is tough for a number of reasons, and I'm not going to be able to go through this one in too much detail because I would be here for hours, but we'll still do a good chunk of it. So basically we want to find the area under this parametric curve that we've got here, and it's between 0 and 4. And so I think the first thing that I'm going to do to try and get towards this is find out what A is. Well, they're saying it's between 0 and 4, so 0 is probably when t is 0. Let's find out what A is when t is 4. Sorry, not when t is 4, when x is 4. So I'm going to try and find the value of A. That is when x is equal to 4. I'm going to try and find out what t is equal to, and I can find out what A is in that top part of the integration. So if x is 4, I can replace it with my 4 equals 8 sine squared t. I'll divide by the 8, which is a half, and then I'll square root. It could be plus or minus, but because t is between 0 and pi over 2, it's just going to be the positive one, because we know that sine between 0 and pi over 2 is always positive. And when you do the inverse sine of root 2 over 2, you get pi over 4, which means that A is pi over 4. In other words, what we're saying is that at the origin, t is 0, and at that point there, t is equal to pi over 4. Hence, we're integrating between 0 and pi over 4 for that part that we've got. Okay, and then what we're going to do is actually go about finding this whole horrible thing that we've got down here. So, to do parametric integration, you do, instead of y dx, you do y dx dt, and it's between 0 and pi over 4. So this is y, and x is up here, and I've differentiated it to get this, which is why I've now got that in place of dx dt. Then I expand these brackets, so I have these two and these two, which come up with these expressions here. And then what I need to try and do is start manipulating it to make it look like the thing that was given to us in the question. And this is where we start using the double angle formulae. So one of the double angle formulae is this, is that sine 2t is 2 sine t cos t. And you'll see in this question that we've got about here, I have the sine t cos t and the sine t cos t. I just don't have the 2. So what I do is I borrow a 2 from the 32, meaning it becomes a 16 here, and then I can actually replace this 2 sine t cos t with a sine 2t that we've got here. And the reason I'm doing that is because I'm trying to go towards this 4t that we've got here. This thing is already in the answer, so I don't touch it, and I just leave it. Now when I get to this stage, I can see that this sine 2t times sine 2t is the same as 8 times 2 sine squared t. I then use the double angle formula for cos 2t, which you should really have memorized, to get that my 2 sine squared t I can replace here with this bit in the bracket, which is 1 minus cos 4t. Obviously the angle needs to double, because when you go from t to 2t, we would go from 2t to 4t, because it's called a double angle formula. Expand the brackets and you come up with the thing that they've got. Not easy. My students that came out from the exam, even the ones who I knew were going to get A stars, they still found that super tough. And then the last part of the question is actually just to finish it off and do the integration. So I would hope that people could have tried to just do those 4 marks, just working out what A was, even if they couldn't do those 5 marks. Anyway, we integrate this, this, and this. This one uses the reverse chain rule because of the fact there's the cos t there. Maybe people found that very tough in this question. And sub in your pi over 4 in all the places, sub in your 0, and you come up with the correct answer of 2 pi plus 4 root 2. Okay, we are now into the top 5. The top 5 kicks off with an AS topic, which I think is rather interesting. And it's from 2020, paper 2, and it was only 20%. So it was a circles topic. And here's the stuff where I think people tripped up on this question. It is a circle with radius r, lies only in the first quadrant. Maybe you forgot, maybe people forgot how to label the quadrants. The first one is where they are both x and y are positive. It goes first, second, third, fourth. It touches the x-axis and it touches the y-axis, so it looks just like this. And we know that there must be r, the radius must be the x and y coordinate. So the centre must be r, because it just touches it. And we know the radius is r, so I can come up with the equation of that circle. It's x minus r squared plus y minus r squared. It equals r squared. And then it says the line L has this equation, show the coordinates of the intersection, satisfy this. So the intersection of this with this basically just means simultaneous equations. So what I did is I rearranged it and I substituted it in place of y that we've got here. Then they want you to do some rather long expanding brackets. That's all of this thing that I've done red here. I don't know if you've ever done that before, but you can use like a grid method to help you do expanding of brackets. And it gives you all of these different values that I've got in purple, which I was able to write down in here when I expanded everything. Some very careful collecting of like terms, a bit of factorizing, so I have my x terms and my constant terms at the end. And then we do come up with this part that we've got here. It then says, given also that this line that we're talking about is a tangent to C, find the two possible values of r, giving your answers as fully simplified surds. So we've kind of already got this sort of like quadratic that we've got here, which is the result of two things being solved together. And if it's a tangent, then I want this equation, I want the discriminant to be 0. So that's what I then go about doing in this part of the question. I make the discriminant for this quadratic, which is not the original one. This is kind of like the offspring quadratic is what I sometimes have called it before. And we take our values of b, a, and c from this one. We put it all into b squared minus 4ac. We come up with this quadratic here, and we can put it in our equation solver for that. And we come up with the two values of r that they wanted. So this question I think is hard because it's towards the end of the paper, and the algebra in this is very, very tough. It makes you feel like you're doing something wrong because it's just so messy. And I think that's often what can happen in these kinds of questions. Okay, we're coming into number 4 now. And there is some parametric equations here. And with parametric equations, this one is from 2021, paper 1, and only 19.7% of people got this right. Now, when people have done this before, what you usually do with parametric equations is people normally say, oh, you're just going to kind of like make t the subject, and then you just kind of like make them equal to each other. So you'd make t the subject of this and t the subject of this. You get those two things and make them equal to each other and hope that it becomes this thing. But they've already given us what the answer is. They've already told us this. So instead of doing t the subject and then trying to make them look like this, you can just substitute x in here and substitute y in here, and you should just show that it's equal to 4. So let's just quickly work through that, and this is kind of nicer for a show that question. It's a good technique to use. I've got x minus 3, so I'm going to do it a bit at a time. I've got my x, I'm going to minus 3, but obviously I needed to have a common denominator here. Combined it all into one thing, so I had the minus 3t squared and minus 3, and that simplified to this. I then squared it by just squaring the numerator, and I just left the denominator with that in brackets. So that's obviously because my 2 minus 2t squared, all squared, ends up as being that thing that we've got there. And then y squared, which is the next thing that I needed, is just 16t squared all over that part on the bottom. So all I need to do now is just do the full substitution. Hence, x minus 3 squared is this, plus y squared, which is this. And we come up with, when they add together as a common denominator, notice how I did not want to expand those brackets. I was able to just add them all together so that it became a plus 8t squared rather than a minus 8t squared. Obviously, minus 8t squared plus 16t squared is 8t squared. Now, my last part of this question, which I probably could have done an extra line in here, and I think I will, is I factorised out a 4 in the numerator, which is great because that's what I was aiming for in the question. And I could see that this left me with t to the power of 4 plus 2t squared plus 1. The last thing to recognise is that this thing that we've got here is equivalent to that thing because they're going to have to cancel. And it is, because t squared plus 1 squared is t to the power of 4 plus 2t squared plus 1. And so those things cancelled, which left us with the answer of 4. So I know why people did badly in this. They did badly in this because they had learnt the traditional way of doing parametric equations, which is to make t the subject in both of them and make those two things equal to each other. But they gave you the answer, so you could just substitute straight in and you would be able to solve this, okay? Just show that it was equal to 4. Okay, we're into the top 3, and I am not surprised this question is here. It is another differential equations question, and it is kind of similar to the balloon question from earlier on, only 14.3% for the average. Pretty crazy, and again, it's from one of those COVID papers that we have. So you might want to pause it and read through it, because I'm going to start going straight into this question. But we basically got this tank. We don't know the height of it. The tank is going to be filling up or leaking with water that we've got. And they tell us a few different things. So they've told us the depth of the water is h, great. Water is flowing into at this rate. So I can say the rate of change, because it's meters cubed per minute, the rate of change of the volume is 0.48. And it's leaving the tank at a rate of 0.18 meters cubed per minute. So this time I put a negative with it because it's leaking or it's leaving, which means the overall rate of change of the volume is meters cubed, and per minute is rate of change per dt, is 0.48 minus 0.1 h. And then the first thing is it wants us to show this kind of thing is true. So basically, what is dh dt? Well, it's reminiscent of that earlier questions that we had where we did the connected rates of change. I've got the dh dt, so I would write dh dt, and the other parts are dv. Now, dv dt is the thing I just wrote down here, so that bit is good to go. And then we just need to think about what's the volume as a formula in terms of h. Well, that's pretty much GCSE stuff, right? It's just 8 times 3 times h. 8 times 3 times h, which is 24h. So I'm going to find dv dh by differentiating that, just goes to 24. And so dh dv is the reciprocal because, you know, the letters have switched around. So we come up with this. All I did is multiplied both sides by 24, then I multiplied both sides by 50, so I wanted that 1200 that was there, and we came up with the thing that there was. Now I actually think that was the easy part of this question. This part, the 6 marker, is where I think people would have found this really tough. So it is a differential equation, which means what we're going to do is we need to collect the h terms onto this side, and the other bits, the dt, is going to go up to the right-hand side. Now, the thing that's probably people would have tripped up on is they would have thought, oh, I can just plus the 5h to this side. But you can only do this using division. So I've divided by the 24 plus 5h, which left me with 1. I then put the dt up here and integrate both sides. Not going to go through the details of integration, but it comes up with this for the integration of this, and 1 integrates to t, and obviously you still have your constant being added on. And then we go and use the bits in the question that they told us about. They told us something that when the tap was opened, the height was 2 meters. When the tap was opened, the height was 2 meters. Sub it in and it tells you what c is equal to. The rest of the question just becomes a lot of manipulation of logarithms and checking that you know how to do all of those kind of things. So I'll just quickly talk you through that. There's our plus c. I put it to the other side and factorized it. Log laws with subtracting meant it could become a divide, and also had to divide by the 240. Then I changed it from logarithms to exponentials. I took the reciprocal here, so this flipped over, which meant the power went from positive to negative. I then simply rearranged it to make 5h the subject, which came up with this, and then divided everything through by 5. Nasty bits of algebra though. Then it says, given that the tap remains open, determine according to the model whether the tank will ever become full, giving a reason for your answer. Now they let you answer this in a lot of different ways, but this is the way I think about it. If the tap remains open, the time is just going to keep going and going and going. So time is going towards infinity. And in the formula that we've got, if the time goes to infinity here, because it's negative, this thing is going to go to a 0, which means the height is just going to go to 4.8, because this whole thing there is just going to kind of disappear. So the height goes to 4.8, which means there is going to be less than 5 meters, so it never fills up. It's only ever going to fill up to a maximum of nearly 4.8, basically 4.8 meters. I say nearly because it will never quite reach it, but in reality, I guess it would do. Okay, so we are now at number 2 of the top 10 hardest questions, aka the top 10 worst performed questions in A-Level Maths from Pure. And it is a proof question, and look how simple this proof question is. Now, it is question 16, right? It's question 16, so I think a lot of people in 2020 ran out of time and didn't get a chance to think about this. And this is why I wish they put this question, or the proof questions, at the beginning of the paper. Plus, maybe people just think proof is hard because people don't really know what to do. But this is a classic one that they have asked. I think this one does have one thing that's kind of similar to it that I've seen in the textbook, but I always make sure I show my students this kind of proof. 6% was the average mark in this question. Pretty crazy, hey? So we're going to prove that the square of any natural number is either a multiple of 3 or one more than a multiple of 3. Now, usually in these kinds of questions, you would say like, oh, cool, it's, I'm going to try and split it into my odd numbers and my even numbers. But the reason you can't do it with odds and evens is you'd have like 2k and 2k plus 1. How are you ever going to end up with something to do with 3 when you're squaring it? There's like an inherent 3-ness to this question that would not work if you did like 2k squared, you'd get 4k squared. And if you did the odd numbers, you'd get 4k squared plus 2k plus 1. None of those got anything to do with 3, so they don't work. Instead, what we do is we split all of our numbers into multiples of 3, one more than a multiple of 3, and one less than a multiple of 3. That's still splitting the numbers up into different categories. We're not splitting them into like odds and evens, but we're splitting them into these. And just to kind of prove to you that it like works with any number, if you think of even like the number 31, well, that's one more than a multiple of 3. If you think about like the number 17, well, that's one less than a multiple of 3. Think about the number 24, well, that's a multiple of 3. Any number will fit into one of those 3 categories, okay? So all we need to do now, if k is a positive integer, we've got 3k, 3k plus 1 and 3k minus 1. We'll just investigate what happens when we square them. So when we square this, we get 9k squared. Yep, it's a multiple of 3. When we square this, we get that it is one more than a multiple of 3, because you've got this as a multiple of 3 and there's that plus 1. And when you square this one, you get that it's a multiple of 3 for the beginning part, but it's also got that one more. And we had to prove that it was either a multiple of 3 or one more than a multiple of 3. Now, if we just got up to this stage, we would have only got 3 out of 4. You do have to have a bit at the end. They said as a bare minimum, it needs to be like a tick. But in this case, I'd have just said, hence we've proven the statement. And I thought in this case, I wasn't going to write the whole thing out because, it's question 16. We're running out of time in this video and people would be running out of time in the exam as well. So the last question, the hardest question that has come up in Pure, or perhaps it was just the question that was done the worst on, is a proof by contradiction from 2020 paper 1. This was also from 2020 paper 2, so people absolutely just did terribly. They flopped on these questions of proof. And I get why. Proof is sometimes a bit stressful because you don't know what to do. But I also think it's something to do with the fact it's question 16. Let me know what you think, whether you think it's because they're hard or whether it's just because they're the last questions in the paper. So it's a proof by contradiction that there are no positive integers such that this thing here is true. So as you know, for a contradiction one, we always start off with the assumption of the opposite. So we'll assume for contradiction that there are positive integers, p and q, that this thing is true. Now, when I do these proof by contradiction questions, I always just say, do something. Like, if it's logarithms, combine them. If it's this kind of thing, think, what could I do? It's usually factorizing or something like that. And I've written DOTS, I hope you know what I'm meaning by that. The difference of two squares. So I factorize this thing on the left and we come up with this. Now, because p and q are integers and because it's going to equal 25, we have to investigate what this could be. So it could either be 5 times 5 to be equal to 25, that's one of the ways you can get 25, or 25 times 1. Now I could investigate 1 times 25, but obviously this one is bigger than this one because of the plus, so I'm just going to investigate the 25 times 1. So one of the things would be if that was equal to 5 and that was equal to 5, but when you solve that on your calculator simultaneously, neither p and q are positive integers. And if you investigate the other one, where 2p plus q is equal to 25 and 2p minus q is equal to 1, you get that p is 6.5 and q is 12. So p is not an integer. So we've kind of got this contradiction here. We assumed that they are both positive, that there are positive integers. Well, there isn't here, and there isn't here. So we've contradicted our assumption. And so here's our conclusion for that final mark. There are no positive integers such that P and Q such that 4P squared minus Q squared equals 25. Now, I guess kind of my thing I'd like you to think from this is learning proof questions are a great way to stand out from other candidates. You can't learn all of them by heart. Some of them are about like having that intuition of what you need to do. But look at these 4 marks and these 4 marks as opposed to, say, some of the 4 marks that we've got, like, or the 3 marks here, or I'm particularly thinking of like some of this really, really hard algebraic stuff that we've got thinking. So maybe it'll give you some stuff to think about how you want to do your revision and what's going to be important for this. So if you did find this useful or interesting at least, do let me know. I'd love to hear about some things in the comments. If you can like the video, it's always nice just to kind of help the algorithm get some other mathematicians to see this video. And if you are struggling with anything with your A-levels for maths or further maths, go and check out my channel page. There is so much stuff there, from like teaching you the concepts really deeply to like tips about exams. And if you're doing further maths as well, there's tons of things there for you as well. Yeah, last of all, just like good luck with all of your studies, and I hope to hear from you soon. And yeah, thanks for watching.